So this video is going to be about resistivity and some of its properties, and also I'll throw in something about the power dissipated by a resistor. It's important to distinguish between resistance and resistivity. Ohm's law allows us to find a relationship between the two of them, and I did that in the previous video or the one before that. And that is, the resistance of a specific sample of wire is something called resistivity, which I usually write as rho res, times the length of the wire divided by the area of cross section of the wire. So as you can see, the resistance depends on length and area. If I have a wire, usually wires are circular, but they don't have to be, and that wire has got a certain length, I'll call that length L, and if the area of cross section is called A, then as you can see, the left hand side does depend on how much of wire you have. If you have a smaller length of wire, your resistance will be smaller. If you have a cross section of area that is small, the resistance will be higher. So thinner wires have more resistance. Now there's something called the American wire gauge, AWG. Higher gauge numbers on the AWG correspond to thinner diameters and hence smaller areas. So smaller areas correspond to higher resistance. So the thinner the wire, the more the resistance per length. So this is the formula for the resistance. Resistivity is a property of the material. So for example, the resistivity of all copper is the same. If you have any kind of copper, so if you have a copper glass from which you drink water, or you have a copper wire or a copper doorknob, the resistivity of all these things are going to be the same. The resistance, though, depends on both the length and the area of the sample. Now, what else can affect resistance? Resistance can be affected by temperature in the following ways. When you heat up a sample of wire, it's going to expand. Everybody knows that when you heat up something, it expands. Well, what's not usually known is that when you heat something, it also becomes bigger in diameter. And so the area also increases. So not only does the length increase, but the area also increases. So there's a contest here. L increases by a little bit, but area increases by a little bit more. So the overall resistance will be changed. Now, depending on the temperature, if it's going up or down, the change can be either bigger or smaller. What about resistivity itself? Does that depend on temperature? It turns out that for many substances, including copper, the effect of resistivity on temperature is bigger than the effect of simply expansion. Now, there are certain materials for which the two are competing. For example, the resistivity changes with temperature around the same amount that the length and area change with temperature. And in one of the problems of this week, I'll have you investigate some materials like that. But right now, we're just going to focus on the property that resistivity itself depends on temperature. And that's captured by the phenomenon of the temperature coefficient of resistivity. It's defined as follows: the change in the resistivity divided by the resistivity at some reference value, which I'll call rho res naught. That's going to be equal to alpha, this coefficient of resistivity called alpha res, times the change in temperature. The change in temperature is either measured in degrees Celsius or degrees Kelvin. So this gives us the percentage change in resistivity as a function of the change in temperature. If I want to expand this out, I will get rho res at a given temperature minus rho res at this reference temperature, which I'll call T naught, divided rho res naught really stands for rho res at T naught, So rho res at T naught is going to be equal to alpha res times some temperature T minus T naught. So that would be the full form of that expression. Now from the units, it's very clear that the units of resistivity, if R is measured in ohms and length is measured in meters and area in meters squared, that's going to be meters over meters squared. So the units of resistivity, rho res, are simply going to be ohm meter. Now what about alpha res? That's a fraction, so it does not have any units. Alpha res should times delta T also will have no units. But delta T is measured in Kelvin or degrees Celsius, but the SI unit is Kelvin. So alpha res must be measured in inverse Kelvin. So alpha res units are inverse Kelvin. In one of the labs, I'll give you data for resistance as a function of temperature. Now because resistivity can be written in terms of the resistance, you can also think of this equation as providing you data of how resistance changes with temperature. So what I'm going to do here is I'm going to multiply both sides by A and divide by L. So rho res can be written as R at some temperature T times A over L minus R at temperature T naught, the reference temperature, times A over L divided by R at reference temperature T naught, which usually is a room temperature, is equal to alpha res T minus T naught. In this manner, the equation that you thought was the defining equation for resistivity becomes now a defining equation for resistance. I'll cancel out the A over L's and I'll get R of T minus R of T naught is equal to, I'll pull the R of T naught to this side, so I get alpha res times R of T naught T minus T naught. And finally, I'm going to simplify R of T naught as just R naught. So this tells me the resistance at any given temperature T minus some reference value of the resistance R naught at temperature T naught is going to be equal to alpha res times R naught T minus T naught. Last step is to take R naught to the other side. So I get R of T equals R naught plus alpha res R naught T minus T naught. So if you plot a graph of R versus T, as you will be doing in the lab, then what you will in fact be doing is plotting a graph that looks like this. Y equals B plus M times X minus X naught. That's really what you're plotting from an algebraic perspective, where X is equal to T, Y is equal to the resistance, the Y-intercept would be the reference value of the resistance, and the slope gives you this quantity alpha res times R naught. So it's very important to find alpha res to also divide by R naught in order to find alpha res all by itself. And that's one of the purposes of the lab. Now for the second part of this video, quite unrelated to the first part, I will be discussing the notion of power dissipated in a resistance. Now the reason that capacitors store energy, resistors spend it, is because of the very mechanism of current flow. in capacitors, charges are separated by a potential difference. They're not going to move anywhere. They're just going to stay there. It's like having money in a bank. Okay? You want to spend it, but you have put the money in the bank, so it's there and it's simply stored. Now, resistivity spends because that charge is moving. A moving charge then knocks out various atoms and other electrons in its path, and that causes frictional heating, and that heating shows up either in the form of a glowing of a bulb or simply the warming up of a space heater to warm your house. And in the process, it goes from a higher potential to a lower potential, spending all your energy. So that is why resistors spend energy while capacitors simply hoard it. So if we were to try to develop expression for the power in a resistor, it's going to be the rate of change of the energy, du by dt. Okay. Now the energy in a circuit is going to be, as I said, the charge times the potential difference, or the potential at any point. Now the potential at any point does not really change, so dq by dt is what we need to do here, and that gives me V times the current in the circuit. Now it's my custom to put little I whenever the current changes with time. We don't know yet if the current changes with time or it's constant. In some applications it's constant, in some applications it's not. So I'll use the lowercase I if current is a function of time. Now this is the formula for power, P equals VI. It's very general, and it's true for almost any circuit applications, including alternating circuits. Now, you can write this in a couple different ways, just like you could write energy of a capacitor in a couple different ways. You can write this also in two different ways by using Ohm's law. Ohm's law says for a resistor, V equals I times R. Now, strictly speaking, I should have put the left-hand side equal also to a lowercase v, but I'm not very consistent like that. So I can write the power expression in two other ways. One is I can eliminate v. If I eliminate v, I'm going to get IR times I, so power is going to be I squared times R. This is by far the most popular way of remembering the expression for power, although my favorite way is v times I, because that's true in a lot of situations. So in fact, it's true even when the device is not ohmic. The Ohm's law only applies when the device is ohmic, so the next two formulas are somewhat less general. The other option is to get rid of I instead of V. Suppose you don't know the current and you know the voltage, then you want to get rid of I. Well, that's easily done. I equals V over R by Ohm's law. So that gives me power equals V squared upon R. Any of these three formulas tells you the power dissipated in the circuit. So I'll box all of them, and they all have their utility. Now the one last thing I need to discuss are the units of power. So the power is measured in units called watts by the inventor of the steam engine, James Watt. So let's see what it is. Watts equals, first of all, it is joules per second. And it's also equal to volts times amperes. So there's a lot of ways to remember it. And according to this equation, it's also equal to ampere squared times ohms. And according to this equation, it's equal to volt squared ohms. So all of these give you the same units of watts.